Swayam Prabha. Digital India. Educated India.
Hello all. So welcome to Astrochemistry, and this is lecture 25. So where are we in this course at this stage? As of like lecture 22, we had discussed about how to detect molecules or atoms in space. We started off with that, and as part of that, we were discussing that we need to get light from a star. The light from the star contains information about the molecules present in the star with which it had interacted. Okay, and based on that, we would get the signals, we would get the spectral signals, and we would compare with spectra or the spectral signals present on Earth. Okay, for that, we need to understand the spectrum of a molecule. And so far in this course, how do we define a spectrum? So far in this course, we understand that a spectrum is nothing but a collection of various energies, right, in the electromagnetic radiation. Currently, okay. In this class or the next class, I shall soon give you a more precise definition. Okay, so then like we compare the spectrum of the light obtained from a distant star versus we compare the spectrum of molecules and atoms available on Earth, and if there is a match, we understand that the same molecules or atoms are present in space. This is our broad understanding. Okay, as part of that, we need to understand the features of the spectrum and spectral signals of a molecule or an atom that is present on Earth. Now, as part of this task, okay, right, that is to understand the various spectral features, well, we need to understand what causes the spectral signals, right? And the spectral signals are caused due to a multitude of effects, such as like molecules rotation, vibration, and also their electronic transitions, correct? So this is what we had learned until lecture 22, and in the next two lectures, that is like lectures 23 and 24, we solved problems related to how concepts such as structural concepts, such as a molecule's dipole, a molecule's polarity, etc., will affect what kind of spectrum we shall be getting. All right. So continuing on the same vein, okay, today we shall further understand electronic transitions in molecules and atoms. All right. So why is it all done? Please don't lose sight of the major picture. This is an astrochemistry course, and we study spectrum. We study spectra, spectrum, and spectral features, and the associated phenomena, the associated fundamental molecular or atomic phenomena to overall ultimately detect molecules in space. Okay, and so to do something as phenomenal as to detect molecules lying in outer space, we're talking about the interstellar medium, which is so far away from us, right? We're talking about so many parsecs away from us, all right? We're talking about such magnitudes of distance, but using the fundamental principles of science, physics, and chemistry, right? We can do some unbelievable things, such as detect molecules in space with certainty. Are we clear, right? And that is why, we have to go back to the fundamentals. That is to understand molecules, rotation, vibration, electronic transitions, etc., which are all the fundamental aspects of physics and chemistry. And by having a thorough understanding of these aspects, we can connect our knowledge into completely apparently unconnected realms. Okay, right? We can connect it with apparently unconnected realms, and we can make huge progress and understand what are the molecules present in space and how they may form, etc. Okay, so with that big picture clarified, okay, we shall now consider the aspect of electronic transitions in molecules. All right. Now, what do we begin with? Let's begin with this idea called as potential energy surface. All right. We're going to start with this idea called as a potential energy surface. In short, PES. Now, it's actually a complex plot. Okay, it's a complex n-dimensional plot as such, but for the purpose of astrochemistry, it suffices that we understand a simplified version of it. Okay, so we're going to be working on a simplified PES, which is nothing but a plot of potential energy. I'm going to call it potential energy P versus internuclear distance in diatomic molecules. All right. So what we're going to study is simply a plot of the potential energy, right, of the molecule, of a diatomic molecule versus its internuclear distance. All right. So a diatomic molecule contains two atoms, correct? And as a function of the distance of the two atoms, okay, right? Start the distance measured from the nuclei, okay, right? We can plot the potential energy of the system, okay? And this is a simplified version of a potential energy surface. And even with this simplified version, we can get so much information about electronic transitions, which in turn is going to help us ultimately detect molecules or atoms in space. So don't worry about the fact that we are only starting with a simplified version. For our purpose, the simplified version more than suffices. And once we understand the simplified version, it's of course a leap of technique, okay? It's a leap of mathematical and some techniques in physics. We can understand the potential energy surface for much more complicated molecules, but we don't, the insights and the intuition that we gain from the simplified version is enough for the purpose of our course, okay? All right, so on that note, so let's see, what the plot of a P versus a internuclear distance looks like in a diatomic molecule. And when I say diatomic molecule, what molecules come to your mind? Simply we're talking about molecules such as H2, N2, etc., right? I've written H2, N2, ... Okay? So many more molecules. The molecules can be, homoatomic or heteroatomic. That is, they need not be H2 molecules of the type AA or like H2N2. They can also be of the type AB. They can be like HCl, NO, CO, etc., okay? It doesn't really matter. Okay, so let's now look into the plot itself. So on the vertical axis, which is conventionally taken as the y-axis, we're going to be plotting the potential energy in some energy units. The exact units don't matter for our purpose, okay, right? And on the x-axis, we're going to be having the internuclear distance, okay? That is the distance between the center of the nuclei of the two atoms, all right? So this is the potential energy versus R for a general diatomic molecule, okay? The general shape of the curve, okay, right, is of the form, okay, right? And this, is chosen to be some origin, 0, 0, some random origin, okay, along this distance. Now, please know the shape of the curve, okay, right? So the shape of the curve is for very large R. Notice this. As R, okay, tends to infinity, all right, please know that as R tends to infinity, right, your PE tends to 0. Notice this point, it tends to 0, it never reaches 0. These are the mathematical features of this curve, okay, right? I shall tell you the physical picture soon after I describe the mathematical features, okay, right? So this is one thing. Then let's look at the other extreme. As R tends to 0, right? As R tends to 0, your P tends to infinity, right? So as like your R tends to infinity, your P tends to 0, right? And as your R tends to 0, your P shoots up towards infinity. Are we good? Okay. And the last feature to be noticed is that for some at some specific R, okay, right? At some specific R, okay, let's say, for in this case, in this particular case, this particular value R. Let me call this value R naught, right? Your P, that is this the value of the y point here, right? Your P reaches a minimum. What is the minimum? A minimum value, that is, for example, if you look at this whole curve, right? If you look at this whole curve, you see that this is the smallest value of P, considering the sign also, okay, right? If you consider the sign also, the P reaches a minimum, and after this point, it increases again, right? Let's call this, like I'll just call this point, this particular point with the dot, with the big dot here, okay, right? And this is going to be called as x comma y, R naught comma P min, right? So this point is R naught comma P min. So these are the features of the curve, which you can see by looking at the curve itself, all right? Now, what is a natural question that you should all ask me? Well, how do I know this curve occurs, right? And what is the basis for this curve? Are we clear, right? Yeah, okay. So the basis for this curve is that, see, I will just retain this page because I may need to use it again and again. I will delete this page. In the region close to, for example, in the region close to R naught, and P min, right? We can actually get experimental data. Why is it? Because, it's a minimum state, right? It's a minimum. So we can actually obtain experimental data typically based on analyzing the spectra of molecules. Okay, I haven't told what kind of spectra, okay, right? Because the spectrum, recall, can be due to the rotations, vibrations, or electronic transitions. It can be due to any of these three, right? I haven't told you yet how. But so region close to, let's say, we're talking about roughly this sort of a region, right? We can kind of get this information from experimental data. Okay, now regions as R tends to infinity, okay, we can of course get it from experimental data, and we can also get, we can also use various mathematical techniques, okay, based on quantum mechanics and spectroscopy, okay. So we can get this based on experimental data and using some math. And there has been found to be remarkable coincidence, right? That for many diatomic molecules, okay, for many diatomic molecules, this is indeed the shape of the potential energy versus the internuclear distance. All right. So there is experimental evidence for this curve. All right. So as R tends to infinity, okay, as R tends to infinity, this curve, let's say, I'm talking about this region now, roughly, right? Yeah. So this region of the curve, we get the information from, in some cases, right? In some cases, experimental data, right? And the math always, plus. Okay, why am I giving you this information? I'm giving you this information so that you understand as to how exactly I obtained this curve, okay? And when I say experimental data, it is mostly by measuring the spectrum, okay? Are we good? Yeah. So the information about this region, we can obtain by using mathematical models as well as by experiments. This region is also obtained by using mathematical models and experiments. For some molecules, experiments, in many cases, mathematical models. But, for these regions, the regions which are to the left of your R naught and P min, okay, right? Regions where your R tends to 0, we do not have experimental data almost always, okay? No experimental data almost. Instead, we rely purely on math. All right, we rely purely on math. The But notice this, so far I have never given you any physical information yet, any physical picture yet, as to why is it that, in some regions we can get the axis, okay, to the curve from experiments, but why in some cases we cannot get the axis through experiments, and we have to rely on mathematical modeling, okay. We're talking about this part, for example, the sharp rise, right? This region here. Are we good, right? Okay, so this is from experiment. I'll just call it like region A. Region A. This is region A. This is region B. And this is region C. Okay. So A, B, and C. Are we good? Yeah. So now, having explained to you, the mathematical features of this curve, right? And also having explained to you how we get this data to obtain this curve, how exactly we get this curve, okay? For the various molecules, right? We can be experiencing slightly different, different magnitudes of where exactly this minimum will occur, okay, right? But the general shape has been more or less found to be the same, okay, right? So this is what is called as a simplified version of a PES, which is a potential energy surface. Simplified PES, where PES stands for potential energy surface. The mathematical features are all fine, but what about the physical intuition? What is the picture that we get? The idea that we get is that in region A, right? In region A, the molecule is at its conventional equilibrium geometry. Right? Equilibrium geometry. Notice that I never told you, anything about the temperature or, whether we subject the molecule to any light or anything like that so far. Okay. We're just saying that, the molecule is at its equilibrium geometry at any given specified temperature T. I've not mentioned the role of the temperature at all here. Okay, right? For our purpose, right? For our purpose, now because we are concerned with conditions in astrochemistry, and recall, in our earlier discussions about astrochemistry, the regions where the molecular densities in space, they're abundant. What are the temperatures going to be? Are the temperatures going to be closer to zero, or will they be much further away from zero? So what do you think is the answer? The answer is they're going to be much closer to zero, okay, right? So let's consider the same conditions. Let's consider the same conditions for this curve at very low temperatures, all right? At very low temperatures. And because we are considering astrochemical conditions, the pressure is also going to be pretty low, okay, right? So at very low temperatures, in fact, we can call as T tends to zero, okay, right? Let's say, we're talking about like 5 Kelvin, 6 Kelvin. For our purpose, that is close enough to T is tending to zero, okay? Are we all good? So why did I not initially talk about any temperature? Because irrespective of the temperature, this feature is more or less going to be holding good. Okay, that's point number one. And because we are concerned with molecules in astrochemistry, and because molecular density is maximal at low temperature conditions, and in the molecular clouds, as we discussed, approximately, I don't know, some 5 or 10 lectures ago, okay, right? We are considering at very low temperatures, okay? So this equilibrium geometry in region A, right, where we get a minimum, okay, right? In this position, right, the distance r equals r naught is what is called as the equilibrium bond length, right? So this is what is called as the equilibrium bond length of a molecule, which is what is the value for hydrogen atom? Sorry, for the hydrogen molecule. What is the hydrogen atom bond length? Any idea? You don't need to give me the exact number. What will be the order? For the diatomic molecules, I don't care about the exact number itself. The order will be what? Will it be 10 to the power minus 6 meters, 10 to the power minus 7 meters, 10 to the power minus 8, 9? It's of the order of 10 to the power minus 10 meters, okay, right? Which is roughly of the order of angstroms, or 10 to the power minus 10 meters. We don't worry about the exact magnitude because that would depend on the molecule itself, okay? So for now, we understand that the equilibrium bond length would be of the order of 10 to the power minus 10 meters, okay, right? So, and of course, because in this region right here, right, in this region right here, because it's close enough to its equilibrium bond length, right, the energy is at a minimum, right, the potential energy is at a minimum. So therefore, we can perform various experiments on these molecules under these conditions. And that's why, you know, we were able to obtain this data from both based on the mathematical models as well as by actually performing the experiments in region A. All right. Now let's discuss region B. Now, what happens in region B? Well, in region B, we have discussed that the distance of separation between, you know, the two diatomic molecules, they are increasing, correct? So as they are increasing, what happens? You know, the energy of the system slowly raises, as we would expect, right? What is the physical picture here? Well, to understand the physical picture, I will just delete this page and I'll roughly give you so far as to why is it that, you know, closer to this point A, we can get information both based on experiments as well as based on mathematical data. Okay. Now, the question we are answering is how to explain the shape of the curve as we go towards r tends to infinity. Okay, right? How to explain physically as we go from r equals r naught to r tending to infinity, right? In other words, what are we doing? Let's, you know, it'll be will be help in our mission to answer this question, right? If we consider a simple example, take for example a simple example of H2. Now we say that H2 is at its equilibrium bond length, okay, right? H2 is at r equals r naught for that molecule when the net sum of, note this, okay, right? The net sum of electron nucleus, see, you think about it, let's call H2 as H1, H2, right? Now each H1, each of the hydrogens, right, they contain a nucleus and an electron, okay, right? So if we consider the potential energy of the full system, okay, right, the potential energy of this system is going to be due to P, you know, the H1's nuclear and H2 nuclear. This is going to be a repulsive force, okay, right? Next, what is going to happen? We're next going to be having the H1n, right? And then the H2e attractive force, correct? The electrons, you know, are going to be attracted between these two, right? So the nucleus is going to attract this hydrogen's electron, and because they have opposite magnitude, the charges, there's going to be an attractive force. Okay. Similarly, I will continue the tabulation in page 7 here. Okay. So H2 is at the equilibrium bond length when the net sum of H1 H2 interactions is favorable. When you say favorable, I'll explain what the phrase favorable means very soon. Okay. So the PE contains H1 and H2n, H1 and H2e, and also I'll continue from here. Okay. So the next term is going to be H1e and then like H2e. This is going to be a repulsive force, right? The electrons are going to repel each other. And the next interaction we're going to be discussing is the H1N, H2N, H1N, H2E. Yeah. The next interaction we're going to be discussing is H1E, right? H1E and then like H2N. This is going to be attractive, right? Are we clear? These are the four terms, right? The one, the nuclear repulsion, and then the electron nuclear attraction between the two nuclei, then the electron repulsion, and then the electron nuclear attraction between the two other hydrogen, the other way about, right? The rest of the terms are all repetitive. If you consider H1 and 2n, then H2 and 1n is also going to be the same. All right, so we don't need to worry about the labels. So the net sum, okay, right? When the net attractive forces, right, overcome the repulsive forces, we are going to be calling the situation to be favorable to chemical bonding, and we're going to be getting this minimum. Okay, right? Now, having understood this, as we move away from the equilibrium bond length, in other words, when we supply external energy, either by shining light, right, or by increasing the temperature, right? When we shine light or by increase the temperature, what does it mean by increasing the temperature? Well, by increasing the temperature of a system, we are supplying the energy. We are supplying some energy from an external source, so that some energy is given to break the bond. As the bond breaks, initially there's going to be a steep rise. Why is there going to be a steep rise? Because we are going to be doing some bad things to the electron nuclear attractions, right? As the distance between the two nuclei increase, right, the electron nuclear attractive force is going to be getting reduced. Okay, right? It's going to be getting reduced, and then so that shall be the dominant term here. But beyond the point, okay, the two hydrogens, let's say until this point there's a steep increase. But beyond the point, what happens is that the two hydrogens are far away from each other. They are far away from each other enough. They're far away to such an extent that they don't even feel the presence of each other. All right. So there's a steep increase to begin with, and after that, what happens is that there is an asymptotic approach. By asymptotic, it approaches zero energy, but it is never zero. Okay, right? There's an asymptotic approach, and what happens is that each hydrogen, that is H1 and H2, they never experience the presence of each other, right? So overall, right, beyond a certain distance, all right, so beyond a certain distance, H1 and H2 do not even feel the presence of one another, which explains why as R tends to infinity, your P tends to 0. All right. So what did we see so far? We've understood why there is a minimum. The minimum actually exists because of a net favorable attractive force, okay, right, between the various nuclei. I illustrated it using the example of H1 and H2, because that's the simplest case. You can choose any other diatomic also for your purpose. Okay, this is point number one. And we also discussed what happens, as we supply some energy. So as we supply some energy, we can still, in some cases, experimentally measure, what happens to some of the molecules. Okay, right? And we see that at very large distance, they don't see the presence of each other, and that is why there is this more or less a constant meandering, right, towards zero. Okay, right, of the potential energy curve. Okay, and this situation can also be experimentally measured in many cases, and there are also mathematical models. Okay, so far we've looked into the simplified version of the PES. We've looked into region A, which talks about the equilibrium distance, right? And we have also talked about the distance as like R tends to infinity. That is when the bond is getting dissociated. Okay. In the next lecture, we should actually be looking into this interesting region C, wherein, as the two nuclei come much closer to each other. All right. On that note, I shall see you in the next class. Thank you.